Hello and welcome back to the second lecture in our series on the approximate Euclidean traveling salesman problem using quadtrees. So just in case you're not watching this lecture right after the first one, I will be doing a quick recap. If you are watching this right after the first lecture and everything is fresh in your mind, you can skip to around the second minute. So first, what we're doing right now is we're giving an exact solution. Uh, and this is going to be slightly slower. It is going to be in time n to the power O of t, where t is a constant that we have chosen, right? So the definitions we need are, first of all, what is a point set, what is a tour, and when do we call our tour a TSP tour if it covers all the points in the point set, what is the length of the tour, and in the Euclidean setting, anyway, every tour is going to be straight lines that we consider. So the length of the tour is just the sum of the length of those straight lines. And then we finally define the problem itself, the Euclidean traveling salesman problem, which says that we want to find a pi opt, a TSP tour, such that every other TSP tour has length greater than or equal to pi opt. Now, since we are going a divide and conquer approach, we want to look at what our subproblems are. So every subproblem is going to be slightly different from the problem itself in that we don't want a tour as a subproblem. We want a union of paths, right? So the collection of paths is basically going to be the intersection of the big tour with a small rectangle of area. So first we have a half open rectangle, right? It's going to look like this. And then we want to find the intersection of the tour we are going to find with that rectangle. So it's going to be some collection of paths, right? The tour can enter and exit the rectangle a number of times. So k is going to be the points where the tour enters or exits. So it's going to be an even number. And we say that it has to be lesser than t. Right? T is a constant we're choosing. And the sigma is just the order in which the tour enters or exits the points in k. So, right, so this explains what we want to do with this sub problem and how we are going to fit the sub problems together to get a final tour. Then next we define cutting lines, which are basically you for each point in our point set P, you take the vertical and horizontal line passing through that point and you consider those the cutting lines. And the possible edges, and this is because you're in the Euclidean setting, all possible edges are just going to be the straight lines between the points. So we just consider all the straight lines and say that our tour is going to be a subset of these lines. Next, we define what a rectilinear binary space partition is. So this is the idea behind this partition is that it is a partition of the whole space by iteratively cutting bigger rectangles into smaller rectangles using only horizontal or vertical lines. And that at each step there's at least one point, in the from the point set inside each rectangle. And so this gives us a sort of partition like this. And each intermediate rectangle is also considered to be a rectangle in script R. So we consider the smallest rectangles and each individual like bigger rectangle which come from the union of these which were there in the intermediate. And RBSP is said to be t-friendly if every rectangle in the RBSP intersects at most t times, right? So we kind of impose that the RBSP has to be t-friendly, and that is why we say that mod k is less than t, which is we are picking every rectangle to have at most t intersection points. So finally, the theorem of the result of the algorithm is that if there is a constant t such that the optimal TSP tour is t friendly, and of course, so that it depends from RBSP to RBSP the t friendliness. So it says that if there is an pi opt and an RBSP R, so such that RBSP R is t friendly with pi opt. So you can have multiple optimal TSP tours. They don't have to all be the same. But if there is one such that there exists some RBSP that is t friendly, then we will find it and we can find it in time n to the power of t. Right. So now let us get to the algorithm. So this is the algorithm itself, and it does pretty much exactly what you would think it does, right? So we start off with, okay, so first, of course, since we're doing divide and conquer, let us start with the base case. The base case says that if there's only one point in a rectangle, just use brute force, enumerate all paths, right? So all possible sets of paths. So you go from K1 to K2, maybe stop by the path point on the way, right? So, uh, so let's do it. Yeah. So, so let us say that this is my base case and there's only one point from P here. And this is my K, right? So these are going to be my K1, K2, and let us say K was equal to 4 here, right? And K3 and K4. So now one thing I can do is I can have just the straight line from K1 to K2, and from K3 I can go to this point and then go to K4. Right? This is one possible solution. An alternate solution would be that I go from K1 to the point and then to K2, and then from K3 I go straight to K4. So these are two possible solutions. I just pick the minimum length of these two. But in general, we can just enumerate them, and that one point between which of these which of these paths should cover that point. So the rest of the paths just make straight lines from Ki to Ki plus 1. And only for the one which picks the point, we just go from there to there. So in time mod K by 2, right? So there are mod K by 2 possibilities of which path has to have the point. So there are this many of them to consider. And we take the shortest among them and report that as the answer. Right? So that gives us the base case. So once you have the base case ready, the next thing is you want to handle bigger cases where there are more than one point. So then what we do is, so we initialize whatever the best path. So the best length of a path and the best path itself. And next we say that we want to enumerate our all possible subproblems. So let us say that this is a rectangle, right? And it has some points, let's say one here, one here. So it has more than one point. Okay. Now we consider a line belonging to the set of cutting lines, right? So these are the 4 points. So L of P intersection R just tells me that I'm only considering all the horizontal and vertical lines which go through these 4 points, right? So just to show it in a different color, uh, blue will do. So I consider this line, this line, this line, and this. So these are the set of my vertical lines I will consider. Then I will consider 1, 2, 3, and 4. So I'll consider 8 lines, right? So if P intersection R is at most mod P, so I'm going to be considering at most 2n lines, okay? And so I'm going to take this rectangle and cut it using one of these 2n lines to get new rectangles, and I'm going to pick K, which is so E was the set of all possible edges, and I'm going to see where all possible edges intersect that new cutting line, and the path can only cross this line. My TSP tool can only cross this line at those points, and then sigma and sigma 2 are the permutations. So I can arbitrarily choose permutations, right? So first, I need to verify the compatibility of the sigma 1 and sigma 2. So here, what verifying compatibility means, and this is going to be an important thing, right? We'll keep doing this, verifying compatibility. So let us say that this was my thing, sub problem, and I had K1 here and say K2 here. Okay. Now, if I pick this to be my line, um, and I say that, okay, so this was for this sub problem, and now I need to define the K1 and K2 for these smaller rectangles, right? So this and this, and now so this crossing point carries over, right? It has to carry over. This crossing point also has to carry over. So this is the first step of checking compatibility, that, oh, whatever the bigger sub problem had, do these sub problems also have all of those points, because it has to cross at those points. Now let us say that these are the 4 new points that I chose, right? So, and those 4 are going to appear on both of them. That's the next thing to check. And finally, the last thing to check is that if I ignore this line, would it look the same way? So basically, would I get something that enters from here and exits from here? So maybe one possible way of doing that is that first I cross, 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 cross. I need more than 4, I need 5. Yeah. That's one more thing. If there is one here and the other one is on the other side, you need an odd number, right? So this is another thing to check, right? And then it finally goes out here. So there are a bunch of things to check. It basically is just, just checking that it makes sense. I'll leave this as an exercise. You can just sit and see what all you need to consider. Of course, in the lecture notes, I will have written everything that needs to be considered, and a concise algorithm to do it as well. But so this is performing a sanity check that, oh, look, these things aren't too wild and they don't, it makes sense. Basically, that's what this compatibility check is. And now once we have all our compatible sub problems. We solve those sub problems, and right, and of course we're using memoization, so all smaller sub problems will have been solved. And so here smaller just means that this is a this rectangle is a subset of this rectangle, because we know that our property for the RBSP is that if they have any intersection, it has to be a subset. So you have a proper partial order on all these rectangles that are there in the RBSP. So you can just have the partial order given by inclusion, and you can solve all the problems in that order. Right. So this is just to help with making a dynamic program make sense. And so we already know the solution to all smaller rectangles. So this and this are things we already know, these two, right? So we find the optimal solution to both those subproblems, and we check that the sum is there. And then what this part is basically doing is that we're finding the lowest sum of the two subproblems. So we're generating all possible subproblems of this subproblem, finding the minimum sum of the answers of the two subproblems, and saying that whichever path gave me that. So for example, so for this to let us say that this was in fact the optimal path for this case, right? So then what would be here is that this, and this, right, would be the solution to this side, and this and this would be the solution to this side. So now, well, that's going to happen if for this problem, this was the optimal solution, and for this problem, this was the optimal solution. And so I looked at these two solutions, and I said that, okay, the sum of these is going to give me the lowest sum, the lowest for all possible ways I can break this big problem. And by doing that, I just take the union of these two paths, and that is going to be this path. And this, because of my sanity check that I had done here, this is valid, right? The K1 and K2, it all matches. And I report that as, the minimum sum and the path, which gives me the minimum sum. Of course, if I had a K3 and say a K4 here, right, I would have more. And then that would appear here as K3 and K4, and it would come here, right? But the point is that the set of paths that I get is going to be the union of the set of paths of these two subproblems. And I take the minimum sum of those lengths to get the best one. And that is how I'm going to solve this subproblem. And I just return that, right? So that is all the algorithm does. And this is standard divide and conquer. And of course, the only place where it's going to be different is in the first step, where I'm not really splitting a subproblem into two subproblems. I'm splitting my original problem itself, right? This is my whole point set P, and I have to split this original problem into two subproblems. Well, we don't really need to do anything much different here, right? Because, so just think of the bounding box as the rectangle, and the K is just empty here because, well, the path is not going outside its bounding box. The tour is not going outside the bounding box of the point set. It has no reason to. Why would it do this if it could just do this, right? And then we pick all 2n lines which belong to script L of P, right? So all those 2n lines are going to be the possible lines, and then we pick all possible K on those lines and all possible sigma. The only thing that's going to be different is that the sanity check here is going to be slightly different, because what the sanity check also needs to check is that, is it going to give me one connected to, because I don't want something like, this and this. I don't want the solutions to come disconnected. So the sanity check also has to check that, if I do this, I'm going to get a single connected tour, right? So again, in the lecture notes, you'll see it, but I encourage you to try to work it out for yourself to see what all you need to check to ensure that you get a connected tour over there. Okay. Yes. So this is the only difference that's going to be there for generating the first subproblems. And after which, following this algorithm, we can solve all the subproblems, and finally we solve the problem itself. Okay. So the first thing that we need to work out is the correctness. We want to show that, yes. Okay. So for the first assumption here is, okay, so first I'll just state the lemma that algorithm 1 provides the correct set of paths for the subproblems in the RBSP that is t-friendly with pi-opt. So let us say that, this whole algorithm only works if there is some pi-opt, right? So let this be our pi-opt. Let's have a quick drawing of our point set. And I think I'd used purple for the tour before, so I'll just stick with that, right? Yeah, this is a good TSP tour. And now let us say that cutting this first, and then cutting this, and then cutting this, and on this side cutting this. And oh, remember that when I cut it like this, because our rectangles are half open, this point is included in the upper triangle, right? Let's remember that. Cutting this, um, cutting this, and then cutting this, right? So now let us say that this is the RBSP that is in fact T-friendly with, you don't need to say the, it is like you don't need to be unique. This is an RBSP that is T-friendly. I think this is again 4-friendly, but it is an RBSP that is T-friendly with pi out. Yes. So then what this theorem says is that for every rectangle in this RBSP, so this guy, or even this guy, or even this guy, for every rectangle in this RBSP, the algorithm is going to give exactly pi opt intersection R as the solution for the for the subproblem that has R as the rectangle and has the correct intersection points within order. So basically, if you had the correct pi opt in mind and you gave and you fed that as a subproblem for a certain rectangle, it is going to give you the correct thing, right? So for example, let us say that this is the direction of the tour, just to solve the subproblem. Yeah. So now let us say that I took this rectangle as my subproblem, and it said that this is going to be K1 and this is going to be K2, right? And these are the points. Yeah, this is the only point, yes, because both of these are open edges. This is the only point, right? So then it is going to give me exactly this, right? And now even for a bigger case, if I take this as my subproblem, right? If I take this as a subproblem, and then this is going to be K1, right here, and this is going to be K2 right here, and these are the points there, then this algorithm is going to give me exactly this path, right, as the solution to this big subproblem. So that is what this lemma tells me, that if I consider any rectangle in an RVSP which is T-friendly, it is going to give me exactly pi of intersection R as the paths for the subproblem. And now, why is this true? And this is going to be true by, let us say true by contradiction, right? Proof by contradiction that so since it is T-friendly, right? First of all, since the RBSP is T-friendly, we are going to have considered this path, right? Because we are literally enumerating over every tour or every possibility which is which intersects at most T times. Mod k is less than T is the only criteria. So we will have considered this path. And what also keep in mind that we're picking the smallest path at each time, right? So at any time, if we had not picked this path, that means that we found something smaller. But if we did find something smaller, so for example, let us say that let's take a nice green, right? Yeah. Let us say that we found this instead, and we returned this. Well, we would only return this if we said that the green path is shorter than the red path, because we have definitely considered both of these paths. But if the green path is shorter than the red path, then this green path taking the union with this purple path would be a shorter TSP tour than pi opt, which contradicts the optimality of pi opt. So by contradiction, we get that it would return exactly this. Okay. Of course, I have done some glossing over, but this is the general idea of the proof, and you should be able to write it down if you need to. But I hope you're convinced that I will consider the shortest tour, and I will return it because it is the shortest. So now that I have this lemma in my hand, right? Once I know that it is going to return the correct thing. Well, so the next thing is that okay. So actually, I'll say a bit more, right? Because when I look at this big rectangle here, right, I am not really considering paths. I'm considering splits. So I should consider. So the idea is that I will consider this split as one of the splits, right, of the RBSP. Hmm. Right, let's blow it up, right? Let's draw that rectangle big, nice and big. This is worthy of an explanation, and so let me give it an explanation. It's worthy of. So, and I have my K1 here, I have my K2 here, and my points are, let's say somewhere here, 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 here. Yeah. Now, so we know that this rectangle R belongs to the RBSP, right? Then in the RBSP, it has to have split into some two rectangles, right? Yes. Okay. Yeah. So this is actually, think of it as a proof by induction first, right? So this R has to have split into some R1 and R2 in our RBSP, right? And so let us, and that splitting line must belong to, so the splitting line there belongs to L of R intersection P, because we are only splitting the RBSP across these lines. Okay. So then, since we are going to consider every possible splitting line to generate the subproblems, we are eventually going to consider L as well, right? So this was the L in this case, right? Just look at it. This is the L here. So we are going to consider L as well. And since, and when we do consider L, since we are also considering every compatible this thing ordering, we are going to consider, so okay, so I'll just write small letters maybe for the new sigmas, right? So K1, K2 to be for this, the lower subproblem, and K1, K2 to be for the upper subproblem. And we are going to be considering this as well because this is compatible, right? And since we are going to be considering this, for this smaller subproblem, we are going to be considering pi opt intersection R1. So let's call this lower rectangle R1, upper rectangle R2. But the point is that for both R1 and R2, we are going to be considering R1 and R2, which also belong to the RVSP. So we should be getting pi opt intersection R1 and pi opt intersection R2. Since we should be getting, okay, and this is where induction comes in, right? So for induction, I need the base case as well. I will get to the base case, but so we should be getting pi opt intersection R1 as the answer for this, and pi opt intersection R2 for the answer as the answer for this. And now, since I'm getting pi opt intersection R1 as the answer for this and pi opt intersection, in my this step, right, I will be considering the sum of those two as one of the possibilities. So since I am going, so that is why I'm going to be considering this as one of my possibilities, and that is why if I return anything else, that something else has to be shorter, contradicting the optimality of pi opt. Okay, so now the base case. The base case again is when there's only one point inside, right? So we have gone to a smallest rectangle which has only one point inside, and in this case, what was that? Oh, it was okay. R1 is the okay. R1 has only one point inside. So, oh no, it does not. Yes, yes. Okay, I will have to redraw this a bit. I think I have to just add this here. So basically, the technicality is that this point, which was for this splitting line, is now inside the right side triangle. So that it belongs to R. So it's also going to be in R1. So we are just split it here again so that R1 goes into the smaller rectangle. Okay, but yeah. So think of the base case. We are now okay. So we have done this split as well because this point is also in our point set, and now it's. But basically, this is the only point here. Okay, and the tour exists at this point, which is going to be somewhere here, okay, which is K2, which was K2 here, but it's going to be K1 here, and it's going to be K2 here, and it found this, and like this is what pi opt intersection this rectangle is. Let's call this small r because it's a small rectangle, and so pi opt intersection small r, okay, is going to be this line, but okay, irrespective of how trivial this case may seem, right? What I want to think about is that if the answer to this subproblem was anything other than pi opt intersection small r, then in my original solution, I can replace this rectangle with, so I can replace whatever is there in the corresponding rectangle with whatever I found. So let us say that I actually instead found this green to something like this, right? Which happens to be shorter for some reason. I mean, of course, in the Euclidean case, it won't happen, but until we have proof that it won't happen, we cannot assume that it won't happen. Let us say that it returned this instead because this was shorter than just the straight line. And remember that we are going to be considering the straight line. Then that would mean that this is shorter. Of course, an equivalent argument to make is that when there's only one point, we said that we're going to brute force it and only have straight lines. And so here it has to only be straight lines. There are a bunch of equivalent arguments, either by contradiction or going straight forward. The point is that whatever pi of intersection small r is going to be the shortest because there's only one point inside, right? So it would be returned. If there was something shorter, then inside that rectangle in the original RBSP, we can just replace it like this, and that doesn't affect any other rectangle, so the rest of the solution remains unaffected. But this part becomes shorter, and so we're going to get a contradiction and contradicting the optimality of phi opt. So this cannot happen. So we have a base case, we have our inductive case. So this tells us that we are good to go. Okay, so now we have the correctness of the algorithm that if there is a pi opt and there is an RBSP that is key friendly, we are going to get the correct set of paths. And the correctness comes from the fact that the whole rectangle, right, the bounding box itself also belongs to the RBSP. Even if it doesn't, well, did I define it too? I think I should have defined it too. The bounding box itself has to lie in the RBSP. You just consider that and you're done. If I haven't, then let me just add that right now. Yeah, okay, I'm not. I think I might have said it, but I didn't have it. Yeah, because I mean, the bounding box of P is what we are partitioning here, right? This whole square is what we are partitioning. So it is the biggest rectangle. Okay. So now then just going all the way up by induction, once we reach the top, right? And when I say induction here, I am talking about the same partial order that I spoke about when, talking about this. We're going up in this partial order by inclusion. So in the end, we are going to reach the whole rectangle, the bounding box. And when we do, we know that we got the correct path. Okay, so then the next thing we have to find out is the runtime. So now we know it is correct. So how long is it going to take? Yeah. So since we're doing memorization, it's a dynamic program, the runtime is basically going to be number of subproblems multiplied by the time to solve a subproblem. And so the first thing is, of course, the order of the problems, right? For dynamic programming, it is important to it depends on when you're solving a certain subproblem, all the smaller subproblems answers are already with you. And so here that smaller comes by inclusion, right? If like one rectangle is contained in another rectangle, and this gives us a partial order, it's fine. We can just affix any there are multiple total orders we can embed the partial order into, and we just pick one and we do it in that order. The point is that every smaller rectangle has to be done before every rectangle has to be done after all its sub-rectangles. That's a good way to say it. Okay. So now the time to solve a problem. So what the algorithm is doing, it is considering at most 2n lines, right? So it is basically considering 2 into mod L P intersection R lines. So and P intersection R is at most P, and mod P is equal to N. So at most 2n lines are being considered. And for each set of 2n, we are considering at most. So we're considering a subset of E intersection L, right? And since L is a line and E is a collection of edges, each edge can intersect the line at most once. So, so each edge can intersect the line at most once. So the number of points in this set is at most NC2 because NC2 is the number of lines in E. The number of edges in E. So, and we have to consider subsets of this. So since we're considering subsets of this, it's going to be 2 to the power NC2. Oh, sorry. Out of NC2 points, we're considering subsets of size at most t. Yeah, that is what this is why t is important, right? You can't sit around having a 2 to the power NC2. That would spoil our runtime. This is why t is important. This is where t comes in. You are considering subsets of size at most t, and with ordering, right? So, and with the ordering, there's this whole idea of compatibilities. All ordering is not compatible. But I mean, the way we are doing it is that we're just generating every ordering and seeing if it is compatible. If it's not, we're throwing it away, right? There might be a better way to do it by just generating only compatible ordering. So you can think about that if you want to, but it is fine. We are considering all, mod k factorial orderings. Okay. So now, what's the total runtime going to be? So for each small rectangle, right? Let us say we're going to look at most second. Yeah. Okay. So there are NC2 points on L which we need to consider, and we're considering at most t of them. So let's take a summation of an I going from say 0 to t, and we consider all subsets of size I, right? We consider all subsets of size I, and so this is going to be the number of them. So the points can be chosen with repetition, by the way, right? We're not even saying that every point has to be used at most once. It can use each point multiple times, and that's why it's NC2 to the power I into I factorial, right? And this is doesn't it's some it's not too hard to see. Just okay, let's take it this way. I is equal to 0 to t minus 1 NC2 to the power I factorial plus NC2 to the power t factorial, and NC2 is less than equal to n square, so we can just have the sigma is equal to 0 to t minus 1 NC2 to the power I factorial plus n to the power 2 whole to the power t, which becomes n to the power 2t into t factorial. Okay, so this gives us one of the n to the power 2t t factorials, then the other one comes from this summation, because we can say that each of these individually is lesser than the highest one, right? So we notice that this is an increasing function in I, and so it's going to be less than equal to NC2 to the power t minus 1, which is the highest possible value that I can take, into t minus 1 factorial. And so this is going to be n to the power 2 t minus 1 whole factorial. And there are also up to t minus 1. And there are t minus 1 terms of this, right? So you're just adding t minus 1 terms, which are all lesser than or equal to this, plus n to the power 2t plus t factorial. We should write that there as well. Yeah. And now, yeah, and again, so less than equal to, I can just, instead of t minus 1, I can just say t over here and here also, right? We're going to make it less than equal to. And t into t minus 1 factorial is t factorial. So n to the power 2t t factorial plus n to the power 2t t factorial. You can notice that this is a very generous upper bound, but the point is that 2 n to the power 2t t factorial is an upper bound, and it is n to the power of t, right? So the number of subproblems we are considering, and well, so this is all the possibilities for one of the subset problems, and like for the other subset problem, it's also going to be n to the power of t possibilities, and we multiply them to get n to the power o of t, because o of t plus o of t is o of t, and there are 2n possible ways to break it into this, so it's going to be so this whole thing is we have to do this whole process. We have to do 2n times, one for each line. So it is going to be 2n into this. Yeah. So and 2n. Well, if you really do want to do it, yeah, you don't really want to do it. You can see that this is still n to the power of t. I mean, so this n is going to get subsumed into this and become plus 1, but o of t plus 1 is still o of t, and 2 is a constant. So it's n to the power of t. So time to solve a subproblem. n to the power O of t. Good. Now, number of subproblems. So, okay, let us look at our big rectangle, and then we have our L of T, right? This is the possible cutting lines. We'll draw some cutting lines. I do the cutting lines first, and yeah, you understand. Yeah, and like let us say that, like for example, these are the points, and that's where these are the cutting lines. Yeah. Okay. So now one more thing is, since we're only cutting using the cutting lines, you will notice that any rectangle that we consider at any point in the algorithm is going to be from these cutting lines itself, right? It's going to have its boundaries as these cutting lines. We're only going to consider such rectangles whose all four sides come from cutting lines. There is no way we would consider any other rectangle. So since there are only n vertical and n horizontal cutting lines, yeah, so since there are only n vertical and n horizontal cutting lines, for any rectangle, there's going to be NC2 choices for uh, the vertical edges, and NC2 choices for the horizontal edges. So there are at most n to the power 4 rectangles that we are going to consider, right? And for each rectangle that we do consider, the possible values of k and sigma are, as we have found here, less than 2 n to the power 2t, right? T factorial. So this is the total number of subproblems that exist. And okay, I mean, it's easy to show that this is also n to the power 2t. Let's just do that. So you get 2 n to the power 2t plus 4 t factorial. T factorial is t to the power O of t. And this is also n to the power O of t. Also, we are assuming that t is a constant. So this is really also a constant, and this is also a constant. The whole point is, yes, the number of subproblems is also n to the power of t. So now the total running time is what did we say it was? Number of subproblems into time to solve the problem. So it is n to the power O of t into n to the power O of t, which is, what is O of t plus O of t? A basic course in probability in complexity theory will tell you that it is in fact O of t. So it is O. So this is the running time for our algorithm. Okay. Now, one thing that I have been very quiet about, been pushing under the rug until now, is why are we only considering lines in N? Yeah. Why are we not considering any lines which are not lines in L? And this is something that didn't come up in the correctness also, right? While doing the correctness, I should have ideally done it and told you. So you said that any RBSP, right? So if there's any RBSP that is T-friendly, we are going to find it. Well, uh, so how can I say that if I'm not considering every possible RBSP? I'm only considering RBSPs who have cutting lines in L. So why I can still confidently say that is because of the equivalence of some RBSPs. Okay, here we are. I have a TSP. I have a point set. Let's draw the whole setup. Right, this is my point set. This is its bounding box, and this is its TSP2 pi opt. Now consider if I do a line here, right? Then this would be the points where it intersects on that line, with this being K1 and this being K2. Okay. How different would it be if I instead draw the line here, a bit to the left? This would now be K1. This would now be K2. K1 was coming from this edge here. K2 was coming from this edge here. Right? Nothing changed. The point where that edge, so right, so E is the possible edges, and the point where this edge, let's say small e1 belonging to E, intersects L, is exactly going to be K2, and small e 2, let us say this guy is E2, where which belongs to L, and wherever that intersects L is going to be my K1. So you see an equivalence between these two, well, sub-problems that I generated. And this is going to carry forward for the whole RBSP, right? So I next do this cut, and then I do this cut. But the point is that, again, this cut is equivalent to having made this cut instead. And instead of the point being here, the point would have been here, which is exactly where this edge, let's call him E3, would have intersected the line, right? So as long as the set of points on each side doesn't change, it doesn't really matter where exactly I draw the line, right? I can actually move anywhere between these 2 points, right? Between these 2 points. All of these lines will have the same thing, like it's going to be the same subproblem of exactly wherever E3 intersects the line is going to be the point K3 and nothing else is going to change. And if I had to solve this subproblem also, right? If this was my, say, my K1 and this was my K2, I would end up drawing this itself, right? Going from K1 to E2 and then going from, oh, why does he do this now? And then going from the point to K2, right? And at the same time, even if this was my line instead, and this was my K1, I would go along the same path here and then go there, right? Because of this straight line business that I'm only going to be moving along these possible edges E, my answer is also going to be the same, and there's the equivalence between the exact subcolumns as well. So this brings up the whole idea of the equivalence of certain RBSPs, right? So some RBSPs are equivalent if, I'm just moving these lines around without changing the exact set of points that are split by the RBSP at each step. And this is why I don't look at every possible RBSP. I instead look at every possible equivalence class of RBSP. Because if an RBSP is T-friendly with PyOpt, every RBSP in that equivalence class is going to be T-friendly in PyOpt by the exact same way, right? And so looking at any one is enough. And to choose the the representative member of each equivalence class, you can choose the one who is dragged all the way down, who passes exactly through this line. Or you can choose who is dragged all the way up, who passes exactly through this line, right? So I think, okay, so when we do half open rectangles where the bottom is included, we are basically doing that, we're pulling it all the way up, and we're saying that this is the line, this dot is still included, this dot is still not included, right? So so this is going to be my representative for this line, for this RBSP. So this is the idea of equivalence of RBSPs, and where you only need to consider the ones which pass through these lines, because it is the same as considering every RBSP who has a line anywhere from here to here. Okay. So with this out of the way, we have finally completed the proof that the algorithm that we stated is n to the power O of t and gives us a t-friendly optimal path. Now, what we would really like to do next, right, to get the exact requirement of the lecture, which is to find betas, would be that if I can say something along the lines of, there always is, some t-friendly PyOpt. There is an RBSP such that every PyOpt is t-friendly. If I can say something like that, then I can find it. Or, well, even better, if I can say that I don't need, now let me just say that pi-t is the shortest t-friendly TSP path, right? Well, basically, what I mean by that is that pi-t is t-friendly, and every pi such that pi is t-friendly satisfies mod pi is less than equal to mod pi t. Greater than equal, sorry. Yeah. So pi t is the shortest t-friendly TSP path, TSP tour. Okay. And PyOpt is, of course, obviously my longest possible TSP tour, which need not be t-friendly. Okay. And okay, when I say a path is a tour is t-friendly if it admits a t-friendly RBSP, right? So this is supposed to be read as pi t has an RBSP script R such that it is t-friendly with pi t. Now, if I can say that mod of pi opt, yeah, okay. So now what I want to say now is that pi t is not much worse than pi opt. So mod pi t is less than equal to 1 plus 1 by t times pi opt, mod pi opt, right? If I can even make a statement like this, then I just set t is equal to O of 1 by epsilon, right? And then in time n to the power O of t, so exactly O of 1 by epsilon, right? I get an algorithm of 1 plus 1, such that pi t, which I found, is less than or equal to 1 plus epsilon times pi opt. And this is exactly the statement of a p-task, right? This is what I want. Unfortunately, statements like this, right, when the t-friendly optimal tour exists, or even statements like this, how bad a t-friendly optimal tour, is not easy to make in the general setting. So we have to make slight changes to the general setting to be able to make a statement like this. And that is what we are going to do when we present the main algorithm. It's going to be all be about how we are going to make changes to the algorithm we just presented to be able to make a statement like this. So it's a good place to stop this lecture. Come back for part 3, where we will finally begin the main algorithm, the approximate Euclidean betas.